Good morning, everybody. Today we are going to finish up with our discussion of the page replacement algorithms, and we are going to start talking about other topics in memory management. Let's do a quick review. Remember, these were the page replacement algorithms that we said we were going to look at, and as we remember, optimal algorithm is something nice that is optimal definitely, but it is not implementable because it requires us to go back and make decisions on what happened in the past. Since we cannot treat the future like the past, we cannot do optimal algorithm. So why do we have this optimal algorithm? It's a good benchmark for us. You cannot do better than that. So if your performance is close to optimal algorithm, then you are doing very good. Question, by the way, how do you measure your performance if you have invented a new page replacement algorithm? How do you measure your performance? What kind of number would you give? So what numbers would you calculate? I mean, what do you look at? I mean, let's say you have not recently used algorithm and the first in first out algorithm next to each other. How would you make your decision? Just a minute. I am not I am for some reason your voice is so, I don't know why. I cannot hear you guys right. Let me see if I can. Just a minute, just a minute, just a minute. Okay, I found it. Yeah, okay, go ahead.
How many times do you have to replace the page per 1000 instruction maybe?
Yeah, oh, sure, yeah. Or you could run exactly the same program with two different algorithms and you look at your page replacement number. Okay, so page replacement cannot be zero because this is virtual memory, right? At least at the beginning of the program loading, program execution, you need to load all those pages from the disk. So you have at least that, but you don't want to replace any pages unnecessarily. An optimal algorithm says that you cannot do better than that, because if you do better than the optimal algorithm, then your algorithm becomes optimal algorithm, because optimal algorithm says that I don't know how you calculate me, but I am the optimal one. Okay, so the key is calculate the page faults. Okay, how many page faults you caused? Okay, if you caused 100 page replacements, page faults for this program, and the other one causes 95, and the optimal algorithm causes 90, then of course you are very close to optimal, and 95 is better than 100, of course. Okay, so these are the algorithms that we looked at. Not recently used algorithm, first in first out, and second chance algorithm, clock algorithm. So these three are kind of the same, right? Their idea is their idea no, not those three, but these three. But where is, come on, yeah, these three are kind of the same, because they have the first in first out basic idea. This is a second chance, a little bit better. Clock algorithm is efficient. Okay, then we have the least recently used algorithm. With this one, remember, least recently used algorithm needs the hardware help, because at each instruction execution, at each memory reference, you need to update the page tables. That can only be done with the hardware. And then lastly, we were looking at this working set algorithm, and that's where we left last time. Today we are going to look at these two. Actually, we looked at the working set algorithm. Remember, working set algorithm says that I am going to keep the working set of the process in the memory, okay, so that whenever a page is needed, I know that it is in the memory most of the time. That was the working set algorithm, and it invented this new virtual clock thing. Okay, let's look at that working set algorithm because the next one will depend on it. With the working set algorithm, this was the idea. You look at this, the working set function W. Okay, this W says that, okay, if you go back k instructions, okay, k references, this is how many pages you need. Okay, of course, if you go back far enough, you are going to reach the number of pages required for that whole application. That's why this is asymptotic function, and it's a monotonically increased function. We know that. Okay, if you have an idea for k, maybe we can measure k in terms of time. Then we can say that, okay, I need this many pages. I need this many pages in the memory for this application. Okay, so that was the working set. Okay, um, and this is how we approximate the working set algorithm. Okay, ideally we would track the last memory references, but that's difficult without the help of the hardware. Okay, but instead we track the pages reference during the last seconds. So we are going to use the interrupts again, timer ticks. Okay, for each page we keep a virtual clock field. Okay, and each clock tick at each interrupt, that is 50 times a second maybe, we update the clock field R if set. Okay, so at each clock tick we update the clock field. Remember, each page has a clock field if R is set, so we are incrementing it. Okay, and if the pages are not referenced in the last seconds, they may be discarded if there is a page fault. And this is one example here. This is current virtual time. Every time there is a clock interrupt, I increment this by 1. Okay, and every time there is a clock interrupt, I check the virtual times of all the pages and update them with this one, because I know that they are all referenced in the last clock interrupt. And of course, I clear out all the R bits. When the time comes to replacing a page, this is what we do. Okay, if R is 1, okay, if R is 1, then that means that somebody has used it during the page fault. I am not going to replace that page. If R is 0, that doesn't mean that I am going to replace it. I am going to look at the age of the page by taking the difference between the current virtual time and the last access time of the page. If it is greater than some threshold, this t, that is the check for the working set, then I am going to increase it. Okay, then I'm going to replace it. Otherwise, if the R is 0 and age is less than some kind of a threshold, then I am going to keep it. So this is looking at the age of the page, and that age is going to give you whether you are in the current working set or not. Okay. Good. Okay, so this is a good algorithm, but it's kind of inefficient. It needs you to scan all the pages and etc. We can make this more efficient by using this clock idea that we had earlier. So this new algorithm is called working set clock algorithm. Okay, so using both ideas, the clock algorithm and the working set concept, we have again circular length of page frames. Okay, and at each page fault, when the time comes to replacing the pages, we check the page R and time pointed by the clock hand. If it is 1, then page is current and that can be discarded. If it is 0, we check the age and if old enough, it can be replaced. Here is one example. Okay, so this is our current virtual time, and these are the times of the last access times of each page, and I am pointing to this page. As you see, the orbit is 1 for this one. Okay, the orbit is 1 for that one, and since orbit is 1, I am not going to replace it because it is being used, it is in the working set. So what I do is I move my clock hand to the next one, like that one. But since I have pointed, I was pointing to that one, I make this 0, orbit 0, so that next time if I see it as 0, I am going to replace it. Okay, so that's the idea. So I am not going to replace this one. I am looking at this one. This looks like orbit is 0, and so what am I going to do? That doesn't mean that I am going to replace it immediately. I am going to take the difference between these two values, the current virtual time and the current virtual time, and the last access time of the page. If it is greater than some threshold, then I am going to replace it. Okay. In this case, it looks like that difference is larger than some threshold. I replaced it, and it is current virtual time. Its virtual access time is the current virtual time. Since I have replaced it, it is 1 now. I am now pointing to this new page. Okay, by new page I mean that the next page in the FIFO, circular FIFO. Okay, so this is the virtual clock algorithm. I am using exactly the same clock idea as before. But remember, with the clock idea, what did we do? We just looked at the orbit, and if orbit is 1, we just skipped that page and we didn't replace it. This one is doing kind of the same. It is checking the orbit, but if orbit is 1, its algorithm is the same. If orbit is not 1, then that doesn't mean that I can replace it. I am going to check the age of the page. Okay, so it is a little bit more expensive than the previous clock algorithm, FIFO based clock algorithm, but it is not much. So it is just a matter of checking the page age, and of course the page ages has to be updated every time there is a clock interrupt. I need to go back. I need to check all the orbits, and if orbits are 1, I am going to update the virtual times of those pages. Any questions? Any questions? Okay, so for some reason we have only 70 people this morning. Or maybe 80 people. $90 people. Okay, as soon as I said, okay. How about this? I have only 90 people. If I told you that you will have a quiz today at the beginning of the second part of the lecture, let me see how many people we are getting now. I bet it's going to be around 150.
145.
150. Okay, let's do that experiment. Okay, we have a quiz today. It will start at 11:30. Okay, so it's going to be for 10-minute quiz. Okay, good. So the questions are going to come from today's lecture, of course. Good, and I need to think up some questions during the break time then. Okay, good. Are there any questions? Okay, there are no questions. So we did not look at the modified pages at all. So how we do the modified pages? You could say that, okay, thinking about the modified pages is easy because if I am going to replace this one, okay, if the modified bit of this page is 0, then I can directly replace it, right? No problem, because it doesn't have to be written back to the disk. That's it. That's as simple as that. What if the modified bit is 1? If modified bit is 1, then this one has to be written back to the disk. So what would you do? You would replace it, and you would write it to disk, and then you could use this page for replacement, right? That's the idea. But no, we are smarter than that. How smart we are? We do this. Okay. If W is 1, I schedule it to be written to the disk, and I keep scanning. So I don't replace this page. Okay. I don't replace this page. Okay. So what do? I say that this page is going to be replaced in the future, yeah, but I am not going to replace it for now because this one has to be written back to the disk. So I am going to schedule it. I am going to tell the operating system that, okay, mark this as a page to be written to the disk, but I am not going to use this for replacement if W is 1. Instead, what I am going to do, I am going to keep looking at these pages to see if there is a page with 0 R bit, old enough age, and W bit is 0. Whenever I find it, I am going to use that page for replacement because replacing modified pages is difficult. Okay, replacing modified pages is difficult. It needs. It takes time. So why do I have to wait for that page to be written to the disk instead of finding a page that is both R and W is 0 and it is old enough? Okay, so that's the idea. That's the idea. If W is 1, then I schedule it to be written to the disk and keep scanning. You might find a clean page. Clean page, what is clean page? Clean page means that, okay, W is 0. So question, what happens if all the W bits are 1? What happens if I cannot find a W bit 1?
It replaces the oldest.
Well, you could do that, but you need to keep the oldest in your memory. But and no, well, I mean, we already decided that this one has to be replaced, right? So we know we know that one of them has to be replaced, or this one or somebody else. Okay, somebody has to be replaced. We know that. We don't have any problem about the oldest or the newest one. The problem is W1 means that we have to wait until that page is written to the disk. So if all the W's are 1, so what am I going to do?
Write the disk before replacing.
So I have to wait until one of them becomes available. So I keep scanning because I cannot use a free page. I cannot use a clean page. There are no clean pages. So I have to wait until one of the pages becomes available. That means that one of them is written to the disk. So I keep looking at the pages one by one by advancing this clock hand. Okay, so I keep scanning. Okay, so that's the question. What happens if the clock hand circles? Okay, if some writes have been scheduled, keep looking. A write will complete eventually. So in that case, I have to wait for the write operation. Okay, other thing is this: if no writes have been scheduled. Okay, what does that mean? There are no writes scheduled. Okay, that means that all pages are in the working set. That's a dangerous situation. Why is that? All pages are in the working set. If no writes have been scheduled, that means that I looked at all the pages. Okay, uh, 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 I looked at all the pages, and I cannot find a clean page to be replaced. That means that I couldn't find any page old enough with an old enough age. Okay, so in that case you pick a random clean page. Random clean page means that W is 0. How about the arbit? What is arbit? Arbit could be 1 or 0, right? I don't know, it could be, okay? But usually we try to pick something with an R of 0. So we just pick a random clean page. But this random clean page is in the working set. And replacing a page from the working set is a bad thing. Why? Why is that a bad thing? Why is replacing a clean page in the working set is a bad thing? What is the problem?
We have to reload it soon.
So what do we call that? What do we call that operation? It's a bad thing, and we have a name for bad thing. It is so bad that they made a name for it.
Is it trashing?
Trashing, yeah. Why is it trashing? Because you are replacing something that you are going to need it in a few moments. Okay? You are going to cause trashing. So how do we prevent this one? Well, in that case, that means that your working set doesn't fit in memory. Okay? You don't have large enough memory. That's what's happening. Okay. Good. Okay. So that's the working set clock algorithm. And let's go back and let's look at this nice table. We kind of looked at this before, but it's kind of giving us the summary of what we had up to now. Our optimal algorithm, not implementable but useful as a benchmark. We said that. Not recently used. Remember what? Okay. Remember what kind of resources they use. Let's remember those. Not recently used. Use the R bit and W bit, right? Remember that. It has classes: class 0, class 1, class 2, and class 3. FIFO, okay. FIFO uses what? It uses what kind of resources? Okay, okay. This one uses the clock too, because at every clock tick, remember, it clears the R bit. How about the FIFO? What does FIFO use? First in, first out. Does it use the R bit and W bit?
No, it uses just the clock.
It just uses the clock. It uses the clock to clear the R bits, right? No, it doesn't use the. No. Where does it use the clock? It uses the clock. It uses the. Okay, sorry.
To track which one came first.
Well, it does. Does it do it that way, really? I mean, FIFO keeps the pages in a linked list, right? So at the front of the linked list is the oldest one. I don't have a clock. I don't keep any virtual clock feeds or anything. And when do I clear the R bit in the FIFO? When do I clear the R bit in FIFO?
There are no arbits in FIFO. There's a orbit in second chance.
Well, yeah, we don't use orbit in FIFO. We use orbit in second chance, right? So this one doesn't use orbit at all. This one doesn't use clock at all. So this one is it just keeps all the pages in a linked list, okay? And whenever whenever there is an page replacement need, page fault, you just replace the one at the beginning of the queue. Okay, that's it. I don't do anything else. I even don't look at the arbit. Okay, but of course, when you get the W, you look at the W bit for the replacement, because I mean you don't look at the W bit to make a decision on the replacement, but you look at the W bit to see if that page needs to be written to the disk or not. Okay, so the second chance, of course, needs the arbit. Okay, it needs arbit because if arbit is 1, then make it 0 and move this page to the beginning of the queue. Okay, so that's what it needs. So who clears out the arbit? Arbit is cleared out whenever I move this page to the end of the queue. Okay, so I do it. Okay, there is a clock algorithm. There is a clock algorithm which is exactly the same as the second chance algorithm. Of course, this one uses the arbit. Least recently used, it needs hardware help. Okay, a new hardware help. It needs to keep a instruction number or the reference number exactly. Okay, so it needs the hardware bit, but we don't like it much because we don't have that kind of hardware support all the time. NFU is trying to kind of doing the crude approximation of LRU. So with the NFU, what do we do? Remember with the NFU, what did we do? We said that we said that with the NFU, we keep incrementing a counter. We keep implementing a counter for each page, and that counter depends on if the R bit is 1 or 0. So it definitely uses the R bit. Okay, but this one is kind of doesn't forget anything. So we have implemented this aging with NFU. Okay, with aging NFU, I always keep incrementing it if R bit is, of course, 1, and I'm doing this division, the shifting thing. Okay, this is R bit again. Oh, okay, by the way, this one is using the clock because somebody has to clear the R bit. Okay, when we come to the working set and working set clock, of course, we need the R bit. Okay, we need to look at the R bit and we need the clock. Somebody has to clear the R bit. Okay, so these are the stuff. So far we like WSClock, working set clock algorithm. Okay, that's a good efficient algorithm to be implemented. Okay, this one never use NRU. It's very simple. It gives me just the idea. Okay, plain FIFO is bad. Okay, but second chance FIFO, the clock algorithm is these are good. Okay, NFU with aging is good. Also, WSClock is efficient and good, gives good results. Okay, good. Any questions about the page replacement algorithms? Okay, as we said at the beginning, where did we said that? I don't remember. As we said at the beginning, somewhere, yeah, here it is. We said that for the page replacement algorithms, I have a few tools: reference bit, modified bit, clock interrupt, page fault interrupt, and advice from the application. So we looked at them, all of them. Advice from application, at the beginning we checked it. We talked about it. We say that maybe the algorithm, the application itself can say that, okay, this is my working set size, and this is my I don't need this page anymore, so you may use it, and etc. Okay, we don't have a specific algorithm for that one, but that's a tool. Okay, good. Let's go back and let's go to some design issues. We kept talking about the pages, page sizes, page tables, allocation, and etc. But we kind of ignored some of the details of the decisions that we have made. Okay, one of them is local versus the global allocation. Okay, let's say we have, it's a good one. Okay, let's say this is our memory, this is our memory, these are the physical page frames, and in my memory there are, I don't know, it looks like there are 16 pages. Okay, and I have three processes running: process A, process B, and process C. Let's say I need a new page for process A. Okay, and these are the ages of the processes, pages, sorry, and 12 means that this is the youngest one. 2 means that this is the oldest page. Okay, so let's say process A needs a new page. It caused a page fault. I need to make a replacement. So if you look at this picture, all those pages here, okay, but that page belongs to process B. If my policy says that you are going to replace your pages locally, that means that only you can replace pages that belongs to process A. Well, in that case, I need to replace this one. That's the oldest A page, process A page. Right? So that's the difference between local versus global. If you are going to replacing this one, okay, this one, then your policy is local. You are allowed to replace only the pages of A, but if you are allowed to change anything, then this one is going to be the replace page. So that's what we mean by local versus global. Which one would you like best? Which one is better, local or global? Of course, there are pluses and minuses of each one. So what is the advantage of global allocation policy?
Maybe it's more efficient if it's done globally, especially if there is one process that runs a lot of page replacements or requires larger number of pages.
Yeah, some processes don't need much pages, right? So give them small amount of page numbers, and sometimes this behavior changes during their run times. They may want to grow or shrink. Okay, if we are doing a global allocation policies, we are doing this automatically, because if a page is causing lots of page faults, I keep replacing the other processes pages, and that's going to give me a nice algorithm, automatic dynamic growing shrinking algorithm. Okay, growing shrinking algorithm. That's the plus side. But the minus side is the one process could become so aggressive that it can get lots of pages, and while the others are using very small amount of pages. That might be the down side, and that would be the plus side of a local allocation. Okay, so when process A has a page fault, where does it get the new page? Okay, if it can get any page in the page table, then that's called global allocation. Otherwise, it's a local allocation. If page replacement affects only the current process, we have a local policy. If you look at all the processes, we have a global policy. Okay, good. So how do you choose it? Usually we like global policies better because it's an automatic way of shrinking or growing your required memory or the allocated memory for a process. Okay, if you use a local policy, okay, and if your working set grows, you need more pages, your process might cause trashing, while there might be free pages available for the other processes. Okay, and similarly, if you are using the working set, if you're the working set, if you are doing the local and if your working set shrinks, you end up wasting memory. Okay, good.
Sir, can I ask a question?
Sure.
If we use global policy, how would you prevent the process from hogging all the memory? Like as you said, some processes might get very aggressive and take a larger portion of the pages themselves.
Yeah, but in that case, operating system has to.
I didn't get the question. Can you repeat it again?
The question is this: if we are using the local policy, how do we prevent a process trashing? If a process needs a larger working set, but if we have only allocated, let's say, A needs to grow its working set, but I have only allocated 6 pages for it, and it keeps trashing while B and C are okay. They don't trash, and in fact, they have a few more pages available to them. So how do we prevent this? But in that case, operating system has to be careful. Operating system has to make a decision on if A needs more pages. Okay, remember what is the second main function of the operating system? Manage the resources, right? I need to manage the resources of memory resources. I have to find a way of determining that A needs a larger working set. Okay, I need to allocate more pages to A. So instead of 6, let's increase it to 8 or 9. So where am I going to get these extra pages? I will get it from B or C. So how am I going to make this decision? Of course, I am going to look at, so what are we after? Okay, we are trying to minimize the page faults. If A is causing lots of page faults, B and C are not causing page faults, then I can safely take some pages from B and assign them to A. So there are some tools that we can look at. The most important one is the page faults. Larger page faults means that, larger than usual means that there is a trashing going on. Okay? If A is causing trashing, then increase its allocated page numbers and take those pages from the other ones. Of course, if I do the global policy, I don't need such a mechanism. Okay.
Okay, thank you.
Good. Memory, maybe this is exactly what you are asking or something similar to what you are asking. The processes grow and shrink. Working sets grow and shrink. Okay. Allocations must change over time. So if you are using the local policy, exactly the same question. So if you monitor the page fault frequency, PFF, it's a term, page fault frequency for each process. Okay. We are going to look at this page fault frequency, and so I'm going to keep a field in my page table somewhere in my memory, how many page faults I have caused, okay, for that process. If PFF gets larger, that's a good indication of I need a larger working set. Okay, I need a larger working set. Remember the parameter, one of the parameters for the working set is tau, or let's make it t. Okay, there is a parameter t. If the age is is smaller than t, then I can keep it. Otherwise, I am going to replace it. So how do I get this t? I make this t larger if PFF goes up. Okay, that's how I make that decision. That's how I make that decision. Good. Okay. So with the local policies, there is always tool. There are always tools to make those kind of decisions. PFF is a good tool for us to make these decisions. Okay, let's go back to the local versus global policies, and we measure the page faults frequencies for each process. Okay, I have this number, page faults per second. Okay, I measure this for all the processes, and usually we have such a curve for each process, and this curve shape is like that, but sometimes it could be like this, sometimes it could be like that. Okay, so it shifts up or down, but the curve is like that. What does that mean? If you allocated too small number of pages for a process, okay, you are going to cause lots of page faults. Okay, we don't like it. Okay, we don't like it. We don't like this area. Why? Why we don't like this area? The rest is red area. We don't like this area. Tell me why.
Page fault is high.
Page fault is high and we don't like it. Why? Because higher page faults means that we need to do lots of disk I/O, right? Okay, maybe it's causing trashing. We also don't like we don't like this blue area neither. Okay, tell me why, Mehmet Selman. We don't like high page faults, but we don't like lower page faults either.
So maybe lower page faults cause other processes higher page faults.
Yeah, we could say that. Yeah, I mean, if we have two small page faults, that means that all the pages of that process is in the memory. Maybe it doesn't need to. I mean, I can tolerate a few page faults per second for any process. That's fine. That's not going to give me a very big hit in terms of CPU usage or the disk I/O, etc. Okay, so we try to keep our page faults somewhere here between A and B.
Wait. Why don't we like low page faults? I didn't get that.
Well, that's kind of an irony, right? I mean, that doesn't sound right. I mean, if you have many processes in your memory, okay, if you have many processes in your memory, and if one of the processes is causing very small amount of page faults, while the others are causing a healthy amount, I don't like that, because that means that that process is using more than enough pages in the memory. So maybe I can take those pages, some of those pages from that process, and assign them to the other process, or keep them empty. Okay, usually what did we say? Usually we like to keep maybe 30% of our pages empty. Remember, let's look at my memory configuration right now, and as you see, okay, where is, yeah, okay, so I am using only 70% of my available memory, even though I have hundreds of processes. Okay, even though I have hundreds of processes, I am using only 70% of it. What does that mean? Even though I have pages available for many of these processes to be in the memory, I don't keep them in the memory because they are not causing any page faults. Okay, they are not causing any page faults. Okay, if a process causes lots of page faults, then I give them more memory, like this one. Teams is causing probably many page faults. It is using lots of CPU. Okay, and it needs lots of memory. Also, the OBS is doing the same thing. But I don't change my available free memory because available free memory is important. If there is available free memory, then I don't have to wait for the writes to the disk. I schedule it for a later write to the disk, and I keep using one of the available memories of it. So that's why we don't like this part. If I am in this area for a process, then I should maybe take away some pages from this process and make it available to all other processes. Make it free pages. Good.
All right.
Okay, it's like the governments. I mean, governments don't like people getting too rich. Okay, I mean that's the way how it should be. Usually, unfortunately, it is not happening that way in today's world. Rich are getting even richer. Okay, but I don't like some people having a very luxurious life while other people are causing lots of page faults. No. Well, I mean, if everybody is in this area, then I am okay. But I know that the world is not like that. Okay, you need to be in balance. Okay, good. So, measuring the PFF, you count the number of page faults per second. Okay, and accumulate this as a moving average. What does that mean? Every clock tick, you know how many page faults it caused that page. So every time there is a page fault, it's an interrupt, right? It's a trap to the kernel, and I know which process caused that page fault. I can count it easily, and I can count this, and I can keep a, let's say, these are my clock ticks. Okay, I say that for process A, I had 10, at this clock tick, I had 10 page faults. For process B, it is 15. Now for this clock tick, I see that it is 15 and 20. This is 15 and 30, 15 and 35. It's going up. So what do? If I take the running average, the running average for A is going to be around 14, but for B is going to be around 30 if you take the average of these 4 numbers. Okay. So the running average is going to give you, of PFF, is going to give you a very good idea for the page needs of that process. Okay. You cannot penalize a process because it needs a larger memory. I mean, that process might be expensive. That process might be a video editing program, and video editing programs need lots of memory. You cannot blame this on the application itself. You cannot say that you are a bad application, you cause lots of page faults. That's the need of the application. And as an operating system, you need to provide resources and the management of the resources for those kind of applications too. Okay, good. Local allocation is global allocation is nice. Okay, it automatically grows and shrinks the pages for some algorithms, but it doesn't work. It doesn't work for the working set algorithm, because with the global allocation there is no one large working set. Okay, and working set has to be for a single process. Okay, so there is no such thing as working set for the whole system. You cannot keep a single simple clock, working set clock for the whole operating system. So what would you need to do? You need to run the working set algorithm for each process, because each process has their own working set. But for LRU and FIFO kind of stuff, it will work with both global algorithms and the local algorithms. Okay, I guess I will stop here because we need a quiz coming up and I didn't prepare my quiz yet. Okay, so
Sir,
yes.
one of the students have written to me and asked me to deliver a message to you saying that they had, although I don't agree with that, they said that they had midterm to hand in at 6 in the morning. So that's probably why most of the students were missing today. So
What
they
what
just
what
want
what course was this?
systems programming.
Systems programming is a third year course, right?
Yes.
Oh, okay.
So they just wanted
Okay,
you
so I
to
will I will delay my quiz to tomorrow then. Tomorrow at the end of first lecture I will do my quiz, okay? No quiz
all
for
right.
today. So we
Okay.
have 112 people. So, oh, okay, it is 111 now. So, Osama, I know it is not you. So,
Yes.
so two people missing, Osama.
Okay.
Okay, maybe so they slept. Okay, so I'll see you in 10 minutes. Let's be here around 11:20,
11:34.
11:34. Okay, Osama, why do you think that they didn't tell me themselves and they choose you as a representative? They
I don't know.
they think that I
S-
like you?
I really have no idea. Somebody wrote to me that can you
Okay.
please tell that to the professor? I said, well, although I don't agree with that, I will I will I will be a good sport.
Okay. Well, I mean, we know that everybody does the things at the last minute. Last minute is the most efficient time of the projects. So
Nope.
we shouldn't do that, but the Turkish culture is always last minute culture. Okay, see you in 10 minutes. Okay, people. So as we said, this decision with allocation of whether being local or global doesn't work with all the algorithms. The FIFO type algorithm, it works for both global and local, but workstation set is meant to work with local allocation algorithms. We keep talking about writing stuff to the desk, but we never talked about where we write them, and are there any design decisions when we are doing this writing operations. This whole process is called swapping. Okay. So let's look at that writing to the disk part. Okay, let's start with swapping. If memory is not enough, what are you gonna do? Okay, I mean, trashing is unavoidable, and we don't like trashing. So one solution to this problem is writing the entire program out to the disk when it is blocked. Okay, if a process is causing lots of uh, trashing, lots of page faults, then it is better to write the whole process, okay, to the disk and block it. Okay, keep it blocked. Okay, then when the time comes when the page faults or the page fault frequencies are below some threshold, you may reload that page, you may reload that process from the disk and let it run. Okay, so this would be one way of compacting the memory, or this could be one way of using memory more efficiently. Okay, so apparently this will free up the CPU, but writing to the disk and reading it from the disk again, of course it will require some IO time, and that process will run very slowly, but it is better than trashing. Okay, if you start trashing stuff, okay, if you start trashing, your computer is very inefficient, because maybe you are using 1% of your available CPU time for a useful thing. 99% is going to be used for handling the page faults. Okay, so it's a good idea to write the whole process to the disk and load it again. But how am I going to make that decision? How am I going to control this swapping? So the idea is, if I have three processes, process A, B, C, and they are all thrashing, that's not a good thing. So I need to make a decision. Which one should I block and write it to disk? A or B or C? This is like a scheduling decision, right? When you do the scheduling, which process should run first? Okay, we said that maybe the process with the highest priority, maybe, yeah, or maybe the process that didn't get the CPU for a long time. I could do that too, but it is a kind of a scheduling question, and we could use the ideas from our scheduling algorithms. So this is kind of two-level scheduling. One level of scheduling is scheduling of the processes in the memory. Which process is going to use the CPU? Okay, that's one level of scheduling. The second level of scheduling is which processes get to stay in the main memory. Okay, and these are two different scheduling tasks, and it has to be handled and managed by the operating system. Okay, for the first level scheduler, our ultimate goal is CPU utilization being fair, okay, not causing any starvation and etc. Okay, but for the second level scheduler, what are we optimizing for? Okay, of course it is CPU utilization. Why? Because if you don't write if you don't write one of these processes to the disk, I am wasting my CPU time. CPU is always busy keep doing writing stuff to the disk and loading them back again. But that doesn't mean we are doing something good, okay? We are spending our most of computer resources for paging in and out. So writing one of them to the disk is going to increase the CPU utilization. Also the throughput too, okay? If I keep all three of them together, it's going to take 10 seconds to compute all of them. But if I write one of them to the disk, it's going to take maybe 2 seconds to complete all of them. So the optimization is for CPU utilization and throughput. Remember, what is throughput? Throughput is the number of jobs that you complete in a given amount of time, such as second or minute. Okay, good. Any questions about this swapping? You swap whole process to the disk and you let it stay there until your global PFF numbers drops down to below some threshold. And after that, you load your process and let it run. Okay, if there are no questions, then we are going to look at this problem of page sizes. We said that, okay, page sizes has to be in powers of 2, right? It could be 2 to the power 8 or 2 to the power 9, 2 to the power 10, etc., or 2 to the power 12. So this 1 kilobyte sizes, 4 kilobyte sizes, etc., they are all possible, and for some operating system they are selectable. So how do we make that decision? What is our page size? So let's look at this one, okay? If my pages are large, okay? If my pages are, let's say, 2 to the power 20, that means that each page is 1 megabyte large. So what is the problem with this page size being large? Page size being large means that the smallest allocation unit in this case is a page, right? If my application A needs, my application needs 1.2 megabytes of memory space, then I need to assign 2 pages for this one. If B needs 1 or 3.5, I need to assign 4 pages for this one. So in total, what I need is 4.7 megabytes of space, but I have to assign 6 pages, 6 megabyte. So what is the problem? On the average, half of the last page isn't used. So I am wasting on the average, I am wasting half of the last page that I have assigned for a process. So if my page sizes are large, then this wasted space will be larger. Okay.
Maybe also if we have large pages, if a program is thrashing, we are spending a lot of time on just writing because we have to write bigger quantities.
That's true too. The cost of page replacement is going to be increased, you are saying, right? That's true. But in reality, actually, I mean, loading 1 megabyte from the disk and loading 16 kilobytes from the disk, of course 1 megabyte is larger, but usually it is the amount of time that you need to move your disk head, rotational delay, and the head movement delay is the amount of the time that you need to spend. So once you locate your head in the right position, this transfer is not that slow, okay? But what you're saying is right. What you're saying is right. So we don't like very large page sizes. So let's keep it small then, okay? Okay. So let's say I have my page sizes 2 to the power 10, 1 kilobyte each, okay? So if I do that 1 kilobyte each, this is 1.2 megabytes. I can assign exact number of pages, an exact number of pages. If I have 1 kilobyte each, so that means that half of the last page is wasted. For two processes, on the average, I will waste at most 1 kilobyte of memory space, okay, instead of wasting 1.3 megabytes of memory space. That would be nice, but so why don't we use very small page sizes then? Well, in that case, the problem is your page tables are going to be very large. Remember, I need to keep a page table, and for each page, there is an entry in that page table. Okay, so for each 1 kilobyte of memory, I need to hold a entry in my memory. That's going to be a problem. Okay, that's going to be a problem. So let's look at this calculation. Okay, let's look at this calculation. We say that our average process size is S. I need S bytes of memory for each process on the average. Okay, you might say that, okay, there are processes and there are processes. How do we calculate this one? And we are going to approach it as using this simple. We are going to use this simple approach. We assume that there is an average process size, and our page sizes are P. Okay, so each process should have S over P pages. That's how many pages you need. So for each page, I need a page table entry, and let's say each page table entry takes E bytes. So this is the amount of memory that you need for that process in the page table. Okay, so that's the amount of memory that you need in the page table. So that's one side. That's the size of the page table. The other one is, we know that on the average, the last page, half of the last page is going to be wasted. So P over 2 will be wasted. So the overhead of paging in terms of memory usage, we are not talking about the CPU utilization here. We are talking about the memory usage, is going to be this: S over P times E plus P over 2. Okay, so let's look at these numbers. If P goes up, okay, let me do it this way. If P goes up, this number becomes larger, but this number becomes smaller, right? If P goes down, this number becomes smaller, nice, but this number becomes larger now. So there has to be a trade-off. Okay, there has to be a nice spot, a sweet spot somewhere. Okay, so how do we solve this problem? Of course, we say that I like to find the optimal value of P. So what am I gonna do? So it looks like O versus P. Okay, and I like to keep O at a minimum. If P is very small, then this number is going to be dominating. So keep P in a nice place. So if P is small, O is going to be large. So we expect something like this, right? And I like to find a spot. So this is a typical optimization problem. This is an optimization problem. And I am going to take the I am going to take the derivative of O with respect to P to find this optimal position. So let's take, so you know how to take the derivative of this one. Okay, this is P over 1. So it is just 1 over 2. That's the derivative. there is this S times E times P over minus 1. So it will be minus 1 will be in the front, and P to the power minus 2 will be the multiplication. S and E will be taken as constants. So this will be my derivative with respect to P. 1 over 2 will come from this one, and S times E over P to the power 2 minus comes from the P to the minus 1. Okay, so what does this give me? This gives me the slope of this curve, and I like the slope of the curve to be 0 so that I can find this tangent, right? So when I equate to 0, I can isolate this P, and I see that P should be square root of 2 SE. Okay, so P depends on size of the process, average size of the process, and the size of the page table entry for each page, and there is a constant in there too, and I take the square root. Okay, so while the memory sizes are getting larger and larger, the need for P doesn't get linearly as large. It gets larger with respect to the square root of this number. Square root of that number. That's why we keep using, I mean, even from 1980s, 1990s, we keep using 1 kilobyte, 2 to the power 10, 2 to the power 12, okay? 1 kilobyte, 4 kilobyte, 16 kilobyte pages for the last 3 decades maybe. Because, I mean, memory size is getting larger, but P is not proportionally growing. Linearly proportionally is not getting growing, okay? It grows proportional to the square root of the memory size of the processes. Okay, good. Any questions on these calculations? Simple calculus math. Take derivative of a formula with respect to P. But we have seen that there's a trade-off here. Of course, this doesn't talk about the CPU utilization. It only talks about the memory utilization. And larger pages are actually, I mean, larger page table entries or the smaller page sizes are problem for the TLB, right? Translation look ahead buffers, and our MMU, because MMU cannot hold many entries in itself. So we like larger page sizes for our TLB buffers and the MMU. This one talks about the memory utilization, main memory utilization only. Very simplistic calculation. This just then gives an idea of how do I design my memory management? How do I choose my page sizes? Basically, I mean, you don't make a decision on your page sizes by looking at this kind of formula. These kind of give you ideas. Usually, you make a decision on your page sizes by looking at the simulation results. You simulate your algorithms on your simulated hardware, like your homeworks, okay? And you count the number of page faults, and you make your decision that way. Good. Okay, let me move on if there are no questions. So far, we assume that there is one global address space for the whole computer, okay? And I keep my data and my instructions in the same address space, okay? we have a single address space that holds both programs and data. Okay, but for some computers, they prefer separating the program space, the instruction space, and the data space. So we call this separate I and D spaces. Okay, and this has some advantages, and we are going to see the advantages in a few minutes. And for each address space, instruction address space and the data address space, of course, we are using caching, and we are using the MMU. Okay, each one will have their own L1 cache place and the MMU place. So separate I and D spaces. That's the idea. So we always assume this is like this: single address space, virtual address space. Of course, we are talking about virtual address space. Okay, I keep my program at the lower end of the address space, and my data is at the top. We usually said that, okay, this part is the program itself, this part is the heap, and this part is the stack. That's what we said. Now we are saying that. Okay, so this is 2 to the power 32. 4 gigabytes of address space for the whole program. Now I have 4 gigabytes of address space for the instruction space and 4 gigabytes for the data space. Okay, so I can have only instructions in this I space, and I can have only data in the D space. So my available virtual memory doubled. I have 4 gigabytes of data space for the instruction and the D space. That might be one of the advantages of it. And the other advantage is I know that all the pages are here. They all have to be clean pages. I don't change my programs, right? I don't have to keep the W bits for these pages, because this is not data. These are all instructions. So the page table that I'm keeping for this part doesn't need the W bits. So this is a little bit easier to manage because I don't have the W bits, and there is no hit for the writing the data back to the disk. I can replace any of them without any cost of writing the data to the disk. For the disk space, the things are a little bit different. Okay, this is one of the advantages. The other advantage is this: think about fork. Okay, after the fork, with this separate I and D spaces, we could do this. Okay, in my process table, okay, let's see, initially I had this process A. Process A forked another process B. I have two processes. What is the meaning of fork? I have two processes running in the memory, but they are exact copies of each other, right? They are exact copies of each other. So if I am using this separated I and D spaces, this is what I do. Both of A and B will point to the same I space. Their I spaces are exactly the same, but their D spaces will be different. Okay, so this is lots of saving, right? I don't have to reallocate this program for both of these programs, A and B, because I know that they are exact copies of each other, and nobody is going to change this program. But data, of course, has to be duplicated because data is going to change. Okay, so that's one of the advantages of shared pages. Okay, pages that are read-only, such as program text, can be shared, but for data pages, the data pages, I have to make a copy. I have to make a duplication. Okay, and of course I could have done this. Of course I could have done this with the regular paging, because remember, for each page, remember what I have for each page. I have this read only bit for each page. Where is it? This is 93. Let me try to find that original page entry. It was way at the beginning, right? Yeah, here it is. Okay, so this is the protection. Protection says that it is read only, write only, execution only, etc. So what I'm saying is that to be able to do this nice fork optimization, I don't need the I and D spaces separated. By playing with this RWX fields, if I say that this page is only read only and it is execution only, then that means that's code, right? I can share these pages between two processes. But so what is the advantage of separating I and D? The advantage is it is much easier. Okay, we say that the whole program is read only and execution, and this is the address space. I don't have to take care of these bits for those kind of pages. It is easier to handle. Okay, it is relatively straightforward. Good. Okay, these are the shared pages. Okay. Nice thing about these shared pages is context switching overhead can be reduced by page sharing. Why? Because if I am sharing these pages between two processes, when I do the context switching, I don't have to reload my page tables for this part of the memory. It is the same thing. Okay, so context switching is more efficient now.
Sir, are these like shared pages the ones that we said when we're talking about inter-process communication that we need mutex system off before entering and exiting?
Well, with this kind of shared paging, okay, yeah, you can do the inter-process communication, because those are the pages that are in the address spaces of two different processes. Yes, you could do this for inter-process communication. In fact, we are going to talk about it, but for now we are talking about sharing of the code. If you do the sharing of the code like this, then you are going to save lots of memory, and you are going to save your context switch time, because for this part you need two different page tables, yes, but for this part the same page table could be used. That's what we are saying. Okay. Sharing data, as you are asking, Osama, sharing data is possible too. I mean, I could share the data spaces. For example, when it comes to fork, right after the fork, I could do this. Both A and B are pointing to the same data space. This is okay as long as both A and B do not modify any pages, right? Both A and B do not modify any pages. If the R bits, or if the W bits of all the pages are 0, then no problem. They can share the same address space even for the data. But if one of the processes changes one of the pages, then I have to duplicate that page. Okay, so in fact this is implemented. They call it copy on write. Okay, after the fork, this is what they do. After the fork, okay, they don't duplicate the instruction space, okay, and they don't duplicate the data space. Both of them are shared, But whenever a process modifies one of the pages, at that time they duplicate that page, not the whole data space. Okay, so this is called copy on write. If somebody writes it, I just copy it. Okay, so this is copy on write improves performance by reducing copying. You might say that this is kind of delaying your copy cost to later. Yeah, it could be, but many of those pages, many of that data will not be modified anyway. Okay, but usually this is what we do, right? After the fork, what do we do? Usually, what do we do?
Execute.
We call execution of some other program, right? So we are not going to use that copy of data anyway. We replace our core image with an image of some other program from the desk. So after the fork, maybe it's the best idea to use this kind of a picture. Okay, don't copy anything. Keep the program space the same. Okay, keep the data space the same. One of the processes are going to change its core image anyway. Okay, so we are going to avoid this unnecessary data copying. Okay, so the initial fork system call is very efficient. It doesn't copy anything. Okay, good. So this approach improves performance by reducing copying. So you delay your write to your modification phases. Shared libraries are using the same idea. Okay. Many programs that I'm running right now, they are using the C libraries. Okay, they are using the C libraries. Many of them doing dynamic allocations. Many of them are doing string processing and etc. And they all come from the standard C libraries. If I keep loading the same C libraries for each process, that would be lots of wasted memory space. Instead, they have invented this idea: dynamic link libraries, DLLs. Okay, so I know that many programs are sharing lots of code. So what do I do? I load that shared code in pages to my memory, and this is what I do. Okay, let's say these are my standard C libraries, Java libraries, whatever. Okay, and in my program, process number 1, this is my process number 1 page tables, process number 2 page tables. I am referring to those pages from my page table and I'm sharing them. Since this is just code, okay, there is no modification. There is no modification of that code, and I can freely share this kind of code. Between the processes, and there could be more than 2, 3, 4, 5 processes sharing the same code. So all you need to do is load that DLL to the memory. Loading of the DLL is done by the operating system, dynamic link library, by the operating system. And by doing this, I am saving lots of memory space. Also, I am saving lots of context switch time in terms of CPU usage. Okay, things are becoming very, very efficient. And whenever a new process starts, I know that many of its code pages are already available in my RAM because some other programs are using them and they have loaded into the memory. These are called shared libraries. Okay, shared libraries are paged. Okay, so shared library routines are located at different memory addresses. So that means what? This code here, when it runs, it shouldn't use any global variables, because if it uses any global variables, then where is that global variable? I mean, is it in that space or in that space? But if this one uses only the local variables, such as the stack, okay, when you say, remember, I mean, when you say I have the stack, if you remember this, where is my where is my compiler? Yeah, here is my compiler. What do I have here? I have add. Okay, here it is. So I don't know what I did here, but is this why am I okay? Let me choose one MIPS stuff. Okay, this is good enough, and get this out, and okay, just simple stuff. Okay, if you look at this one, all the addresses that I'm using is referring to the stack pointer. Okay, it takes that, it says that take the stack pointer, subtract 24 from it, and then store word, and I think this one is for the local variable result, right? This one is for the local variable result, and I move it to this register. As you see, I have this absolute number to be loaded to the second register, and I put it to the FP, and from FP to SP, right? So it always talks about the stack pointer. It doesn't talk about any global addresses. But if I put a global variable in here, integer global 512, okay, and maybe this is global here, okay. So I need to load this address of this global variable into this register, etc. So this one needs a global address, and the global address comes from somewhere there. So this is not a relocatable position independent code now, because it is referring to the global position. But previously it used to be position independent, because it only depends on the stack pointer. And as you know, the stack pointers are saved and loaded whenever there is a context switch. Okay, so if those shade libraries are written that way, no problems. No problems. This will work. And shade libraries are used a lot by Windows, and we have many of them loaded in the memory. And whenever you write a program, you usually prefer making your libraries into shade libraries, DLLs. Good. Okay. Something related to shade libraries, actually the generalization of the shade libraries. Many operating systems, including Linux and Windows, they will give you a tool, okay? Using this tool, you can make a system call to map a file onto a portion of your virtual address space. Something like that, okay? This is your desk. On your desk, there is a file, okay? The operating system will map this file from this position to, no, that's not good, okay, from this position to that position. So all these pages, whenever you access in your virtual memory, are actually coming from the disk file. So whenever I write to that position, you are writing to your disk. Whenever you read from that position, you are reading from the disk. Okay, you are reading it from the disk. If I do the same thing in RAM, okay, if I doing this thing in the sharing in RAM, and this file, okay, is mapped here, and I am going to see this part of the memory, this part, and like that. Okay, good. If I write something to this part, it will be written to the disk. If I write something to this part, it will be written to the disk. So I am using a file as part of my memory. It's called memory mapping, and this could be used as a way of communicating between two processes, inter-process communication maybe. Okay, so you are using your disk as a communication place, and without realizing from your process, you do your disk I/O using regular program instructions. Okay, the idea is same as the shared libraries. With the shared libraries, you are saying that this part of the memory is shared between these two processes. Now again, this part of the memory is shared between these two processes, and that part actually corresponds to this part of the disk. This is called mapped files. Okay, it provides an alternative model for I/O. Instead of doing reads and writes explicitly, you let the operating system deal with those kind of complications. All you see that plays as a large string, character string. Okay. So if two or more processes map onto the same file at the same time, they can communicate over shared memory. They can do the inter-process communication. Of course, that doesn't eliminate any race conditions. To eliminate the race conditions, you have to do the critical regions, okay? Exclusive access, mutexes, semaphores, monitors. Okay? So the idea of this memory mapping is easier with the paging. Okay, as I said before, another topic with the design issues of the memory. Okay. Paging works when there is an abundant supply of free page frames. It works best. Okay. So whenever you need a new page, your page is already available because all the pages, 30% of the pages are waiting for you to use. Okay, so how does this happen? This happens by this paging daemon. Paging daemon is a system process. It just sits, okay, it just sleeps most of the time. Whenever it sees that the free memory is below some threshold, it wakes up. Okay, it wakes up and it swaps out some of the pages to the memory, and it makes them available to be used. Okay, so it makes sure that 20% or 30% of the memory is always available for processes to use. By doing this, processes become very efficient because whenever they need new memory pages, those pages are available. That they don't need to think about finding a page to replace and etc. Okay, so this is the cleaning policy, and it works very well. So you might say that, aren't we wasting 20% of our available memory? It might seem that way, but the experience shows that if you follow this policy, this cleaning policy, your overall memory usage performance and the CPU utilization performance will be higher. Okay, so that's why, I mean, just look at your computer right now. Try to see how much memory you are using. You will not see it as a 100% or 85%, 90%. You're going to see well below those values, because if you are using 100% of your memory, that means that you are very badly trashing. You are trashing very badly. Okay, even 90% is not a very good number. Okay, you don't want to keep your hospital beds 100% full. Okay, if you do that, things are not going to work very well. Okay, you like to keep at least 30% of your beds, hospital beds, always available, so that if there is an emergency, some new patient is coming, it is easy to find a bed for that new patient. Okay, so that's called the cleaning policy. So when do we get involved with paging with the operating systems? Okay, it looks like I'm out of time. And let me look at this a little bit. Tomorrow I will start from this position. Okay, when you have a new process after the fork, okay, of course the operating system has to set up the page table and allocate the spaces. Okay, during the process execution time, when you do the context switch, when you do the context switch, MMU has to reset, TLB has to be flushed. That's why context switching takes lots of time. MMU has lots of data, TLB is filled in, and repopulating these will take lots of time. During the page fault time, operating system has to take control, and operating system has to make a decision which pages to replace. And of course, for the process termination time, I need to release the pages. Okay, I think I will stop here. Do we have any questions? If there are no questions, I will stop here and I will continue from this point tomorrow, and I am hoping to finish up the rest of this chapter and start the next chapter maybe. Okay, see you tomorrow.
Have a nice day, sir.
See you tomorrow.
You too, thank you.